So we're going to be talking about the chemical shorthand, which is the language of chemistry. It's largely a written language, and some of it you already know. I mean, you know H2O is water, you know CO2 is carbon dioxide, because you've seen these time and time again. Well, today we're going to go over a bit more involved. As you can see, my picture here has water, oxygen, and glucose, but we're going to go over a fair amount. First off, everything is based on this law of conservation. Matter and energy cannot be created nor destroyed, only moved and changed. Every chemical reaction follows this. We have to as well, so that we can accurately predict what is going to happen anyway. Nature is going to do what nature does, but we don't want to be caught, unawares and surprised by what happens. As such, we need to make sure that we balance the chemical reactions we intend to use. To do that, we need to speak the language of chemistry, or more importantly, we need to write it. Chemical shorthand is the language of chemistry, and as I said before, you've probably seen H2O before. Who can tell me what H2O is?
Water. Yeah.
Wonderful. So you know. Beautiful. Okay, now with this water, there are some things for you to interpret. First off, there's our representation, and that little 2 there is called a subscript. This tells us how many atoms of that element are there per molecule, per compound unit that we are looking at. So there are 2 hydrogens. So the little 2 is written to the lower right-hand side. It'll actually be like this for you all. If I have a second water molecule that shows up, I do not change this to H4O2. That is not proper, because that would imply that all of those are bonded together. Instead, I put a big 2 in the front. This 2 is a coefficient, which is how many molecules we are dealing with. So the difference between a coefficient and a subscript. You will see this a lot. If I take a look at this 2AlNO23, AlNO23 is aluminum nitrite. You might have gotten that from our lesson last week. And as you can see, the 2 affects everything. The big 2 coefficient affects every little piece of it. That's why we have 2 of these molecules there. The little 3 that is outside the parentheses affects the N and the O, which is these bonds that have now appeared. And the little 2 just affects the oxygen, and that's why we have 2 oxygens attached to each nitrogen. So this is kind of just a graphical way to show you how this works. If I were to write an atom inventory, it would be Al2N6O12, like this. Al equals N equals O equals, and then 2, 6, and 12. That's if I want to take an atom inventory, which you will have to do at times, and then we're going to stop doing it probably tomorrow. You could also have just said there were 6 nitrites, because nitrite is a thing. Polyatomics exist as a single piece, and so we can count those instead of the pieces that make that up if we wish. So the answer then would be Al2NO26. So how many atoms of each element are in the below compounds? So if I'm looking at methane here, and I want to find out how many element is here, okay, I'm gonna just quickly grab my pen and my drawing tool. What I'm dealing with, I've got C and I've got H. There is no subscript here, and in chemistry that means there's 1. We do tend to not like writing 1s, so that would be, there is 1C. And the subscript over here is 4, so there are 4 H's. So 1 carbon, 4 hydrogens in methane. Do you understand that? Please raise your hands if you do, because it's going to be really useless for me to go over if you can't understand how I'm breaking this down. Okay, good. So there's all sorts of practice that is built into this that you may, of course, endeavor to do so. Here I've got P2S4. So this is going to give us 2 phosphoruses and 6 sulfurs, but it asks you also to name it. Since this starts with phosphorus, which is a non-metal, this is a molecular covalent compound, which means we use our subscripts as prefixes. So this would be 2 is di, P is phosphorus, 4 is tetra, S is sulfur, which becomes sulfide. So this is diphosphorus tetrasulfide. And then there's all sorts of practice here. And make sure that I gave a little warning here that your coefficients affect everything, just in case you forget. Here we've got 2 molecules of propane. That is going to give us carbons and hydrogens. This 2 affects both of these. It affects the C and it affects the H. This 3 affects the C. This 8 affects the H only. And it is multiplicative, so multiply. 2 times 3 means there is 6 carbons. 2 times 8 means there is 16 hydrogens and 2 molecules of propane. So that is your breakdown. And you might be like, Mr. D, this is easy. I get this. Why are you spending time on this? You'll see. Over here, doing the same deal, moving the coefficients over. Again, you have 6 H's, 3 sulfurs, 12 oxygens, or because this is a polyatomic, you just count that as 3 because there's 3 of this whole polyatomic. You can do that too. And this is 3 molecules of sulfuric acid. See, this 3 is telling us the number of molecules. So the correct translation of this piece is 3 molecules of, and this is sulfuric acid, which we learned last week on Thursday, I think. All right, parentheses distribute, so make sure you count them together. In this vanadium 5 nitrate, we are dealing with our 3 only affecting this oxygen, but the 5 affects the parenthesis. And since it affects the parenthesis, that means it affects the oxygen and the nitrogen. So as far as V is concerned, well, I only have one of those things. There's nothing to the lower right. It's not in the parenthesis, so that's fine. Then I got my N and my O. My N has nothing next to it, but it is within the 5, so there's 5 of them. And then 5 times 3 is 15 oxygens. I could also write this as V1NO3 5, like that. This is an acceptable breakdown as well, because polyatomics are already bonded together. They act like one thing. You might as well treat them like one thing. Sorry, I don't want to do that. I want to do this. So if I have this, I would like you right now to break down how many N's, how many H's, how many S's are there, and can you name it? I'll give you a minute to do so. Let's break down the N's real quick. If we are looking at the N's, we've got nothing immediately next to it. This 4 does not reach that N. It is affected by the 2, and it is affected by the 5, which means for the N, we have 10. For these H's, you have got the 4, the 2, and the 5. 5 times 4 is 20, times 2, 40. There is 5 S's. There's nothing here. It's not in parentheses. The only thing that affects it is the big 5. Translate 5 NH42S. So we start with the 5. The 5 means 5 molecules. NH4 is ammonium. You should know this from your ions. This also makes it an ionic compound, which means sulfur just becomes sulfide. So this is 5 molecules of ammonium sulfide. And that is the main lesson that you're going to be doing with today, is being able to take the chemistry written and write it out in English, and then going back and forth. That's what you're doing today. Tomorrow we're going to balance. All right, hydrates are a pain in the butt. When we sit there and we look at this hydrate here, my biggest recommendation for you is treat the hydrate like it's its own thing, because it is. But if you have to break it down, then feel free to do so. But you want to do so extremely carefully. So the aluminums are easy. 4 and 2. There you go. Come on, Ben. There you go. You've got 4 and 2. So for aluminums, you've got 8. For carbons, you've got the 4 and the 3. And that gives us 12. But it gets really weird when we get to the O's and the H's. O and H. So let's tackle the O's real quick. For the O's, we first got the O's over here. So we've got 3 times 3 times 4. 3 times 3 is 9, times 4 is 36. But we also have the O's over here. So you might be like, okay, well, there's nothing here. There's no parentheses, and there's just a 2. So there's only a 2, right? Not quite. This 4 also hits that. Oh, that was a horrible line. I can just delete that. There we go. Pretend that didn't exist. This 4 affects the hydrate as well. So that means 4 times 2 is 8. So this is plus 8, which means there is 44 oxygens in this. This is, of course, if you don't just leave it as water. And then for the H's, you've got your 2, you've got your 2, and again, you have your 4. Oh, I see why I'm doing it. I'm sitting like an idiot. I'm sitting all curved to the board. Okay. Yeah, that's a little better. Okay, 2 times 2 is 4. 4 times 4 is 16. Like that. So, pain in the butt? Yes. Can it happen? Yes. Who here can tell me the name of this? Understanding that you should start by saying 4 molecules of, and then the name. Who here can tell me that? The name of this beast. 4 molecules of aluminum carbonate dihydrate. And each and every one of you are supposed to be able to do that. And if you cannot, if you look at that and you don't know how you've got your aluminum, your carbonate, then your dihydrate, this was a beast. This was a hard one. I mean, don't get me wrong. It's one of the hardest ones that I put out there. So there you go. And again, if you kept it in its chunks, you could have answered it like this. 8 aluminums, 12 carbonates, and 8 hydrates or 8 waters also work. So you either break it down by element or you break it down by chunk. I don't care. Either works. 4 molecules of aluminum carbonate dihydrate. All right. 2 important symbols, the plus and the arrow. Plus will mean and, with, reacts with, and others. Anytime we're combining 2 things, you've got a plus sign. The arrow means yields, produces, becomes, reacts to form. This is a transition. It is changing into something else. Now, for this class, there will only ever be 1 arrow in everything that you do. 1. There can be as many pluses as I need, but there'll be 1 arrow, typically near the middle. In chapter 5, as a bonus, I will show you a reaction that has more than 1 arrow. That's called an intermediate, but we'll get to that in chapter 5. That'll still just be extra credit. It will not be something you are required to do. So you're just dealing with 1 arrow per. Now, diatomic elements cannot be alone. Remember, these are our social elements. They are just 2 reactive, and that's hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. And if you're using my periodic table, which you should be using because I put all sorts of great stuff on it, this is in the bottom left of the front of the periodic table. Now, if I have my H2O and I electrocute it, I get H and O that separates. However, you may be like, Mr. D, social cannot be alone, which means that oxygen has to be a 2. But wait a minute, where did this 2 come from? There's no 2 here. Well, that's because you need to balance it. 2 molecules of water are electrocuted to 2 molecules of hydrogen gas and 1 molecule of oxygen gas. So there's double the hydrogen to the oxygens, and this is how we figured out what water was made out of, is we electrocuted it and collected the gas. All right, so pretty cool that we did that. And you might be like, Mr. D, what if there's only one water molecule? It's like next to impossible to get one molecule alone from everything else. So good luck with that. It'll probably never happen. Don't worry about it. But Mr. D, fine. In that case, it probably, if you electrocute it, it'll probably snap right back together, is what would realistically happen. It would separate for the briefest of moments, and then that super reactive oxygen would latch back onto the two hydrogens, and you still have water. Now, an atom inventory. To do an atom inventory, we did them by compound. Now I'm going to show you how to do it by reaction. Write each element in a line down the center of the arrow. Count the atoms on the reactants to the left and the products to the right. If there's the same number of each element on both sides, it's balanced. And that's great. We want balance. Balance is great. This maintains the law of conservation, and everything is happy. In a balanced equation, the number and type of atoms reacted always equals the number and type of atoms produced. Reacted always equals produced, because matter cannot be created nor destroyed. If I look at this chemical reaction, this is methane plus oxygen, gives me carbon dioxide and water. What I'm going to do here is I'm going to write all of my elements in a line down the center of that. It helps if I do not decide to randomly put my pen someplace I cannot find it. Where did oh, I put it where it belongs. I am so foolish. So I go element by element by element. I have carbon, I have hydrogen, and I have oxygen. I write it under the line, under the arrow. I put a dash before and after because I'm going to be counting them on both sides. On my carbons here, I only have 1. For my hydrogens, I have 4. For my oxygens here, I also have 4. When I go to my other side, I look here, I've got 1 carbon, 2 oxygens. Notice I'm literally going down the line. Okay, so 1 carbon, 2 oxygens, write a 2 there. 2 times 2 is 4 hydrogens, plus 2 more oxygens. 2 plus 2 equals 4. 1, 4, 4, 1, 4, 4. This thing is balanced. So this is all you are going to need to do today, is count them and say if it's balanced or not. Tomorrow, you're going to fix it if it's not balanced. But that's tomorrow's lesson. For now, I just want you to count. Now, only do an inventory if the question tells you. If the question doesn't tell you to do an inventory, don't do one. More on that tomorrow. Now, example number 2, we've got ethane plus oxygen gives me carbon dioxide and water. This is also a combustion reaction. Mr. D likes combustion reactions because they're easy and fun. So I've still got carbon, hydrogen, and oxygen on both sides. I've got 2 carbons, 6 hydrogens, 6 oxygens. On the other side, I've got 2 carbons, 4 oxygens so far, plus 6 hydrogens, and 3 oxygens. 2, 6, and 7. Notice the 6 and the 7 not equal. Boom, this is not balanced. Okay, I would like you to try this one out. It's nice and easy. There's only 3 things. You should have had Na and N, separated those out. There's 6 and 2 on the one side and 6 and 2 on the other side because this is totally balanced. If you got that, good job, well done. An inventory, a very basic equation. That's still good. It means you've got the idea, even if you don't have something to do something a little harder. Here is another one. So you should try these practices out. I unfortunately want to make sure we get to the end, so I'm just going to click past this because what I want to see is this. When you do something that has got polyatomics, the SO4 and the SO4, you can break them apart if you'd like, and as you see, this would be balanced, or you can keep them together and count them as if they were one thing, because they are. And if you count them together, You may like put them in boxes and then say, oh, this has got 2 boxes here, this has got 2 boxes there, so there's going to be 2 SO4s. Still going to be balanced, still going to work out. You can do it either way, whether you put them in boxes or you count them individually, but it works. Phase symbols. Phases as parentheses subscripts after the formula. You write it as formula, and then after the formula in parentheses, you write the phase, which will just be a letter or two. S is for solid. Metals and ionic compounds are solid unless you are specified otherwise, except for mercury, which is a liquid unless specified otherwise. L is a liquid, water, bromine, mercury. There's actually not a lot of chemical liquids out there. Most liquid-looking things are actually the 4th one, which we'll get to. Gases are G, and that's most social elements, oxygen, nitrogen, chlorine, as well as things like carbon dioxide. The 4th phase is aqueous. This is when it's dissolved in water. All acids have to be aqueous in order for them to work. Either that have to be melted down, which is really dangerous. So they tend to just be put in water. So if you have an ionic compound and it doesn't tell you anything else, it's a solid. If you have a metal and it doesn't tell you anything else, it's a solid unless it is mercury. If it says dissolved in water or aqueous or acids, it is going to be AQ. You really should only write phase symbols when it tells you to do so. Specifically, that'll be when we translate. When I translate from English into chemistry, I will have you write phase symbols. A lot of times I will not have you write phase symbols. So only use them when you are told to do so, which translations you will be. This is an important symbol. It means with heat, while heated, in the presence of heat. So if there's a triangle above the arrow, that means heat was constantly applied to make this reaction happen. Typically, if there's something on or below the arrow, that is a catalyst, and that is just a chemical that helps speed up the reaction to the point where it can then work in time that is useful. And in this case, the heat, the energy added, is our catalyst. So when you see a triangle above an arrow, that means this sucker was heated. If you look over here, zinc metal and hydrochloric acid react to form hydrogen gas and aqueous zinc chloride. You need to translate this, to take this English and turn it into chemistry. If you do so, you get this, zinc plus 2HCl. You didn't need the 2's because I didn't have that in there. You probably wouldn't, but that's on me. I mean, it is going to be a 2 there, but that's okay. I becomes H2 and ZnCl2. So what are each of these? Well, metals are, oh, you're not going to, oh, I forgot. It's because you're Googleized. You're going to come in at the end. Well, I don't have time for that. Metals are going to be a solid. Acids are going to be aqueous. Hydrogen gas, I mean, it tells it to you right there, but you could have figured that out. And aqueous zinc chloride. So it's telling you that this one is aqueous. Normally, it would be a solid, but it's telling you it's aqueous. Then you need to watch out for a precipitate. Precipitate is when you have a new phase from like phases. If you look at this, iron 3 chloride plus silver nitride becomes iron 3 nitride and silver chloride. But notice, aqueous becomes aqueous and solid. You have a new phase. This is a precipitate. And that new phase tells you that the precipitate is silver chloride. This is the same thing for rain. Rain is 2 gases, hydrogen and oxygen, mixed together to form water. That water becomes a liquid, so 2 gases make a liquid. That is also a precipitate. That's why we call it precipitation. To translate, skim the sentence for direction, then translate each English word and phrase into chemistry. Check for problems. The problems are listed in order of how often students mess it up. Check that your social elements are not alone. That's a big problem. A lot of people will write the social elements alone. Don't do that. Check the compounds. Most of the problems you're going to have is with charge. Your charge needs to equal 0. If it's molecular covalent, charge does not. Just follow the name. That's the easy one anyway. Make sure all your phases are correct and make sure you have symbols, pluses and arrows in between everything. There'll be just one arrow, but there should be stuff in between. What we're going to do then is balance it, but we're not doing that till tomorrow. So for now, you got to do steps 1 through 3. Step 4 will be tomorrow. All right, so if I have this, magnesium metal and sodium chloride dissolved in water react to form magnesium chloride dissolved in water and sodium metal. So first off, I check for directionality. It says that stuff reacts to form other stuff. This is then in the right order. It's saying this is the stuff I started with. It reacts to form this other stuff. So what you're looking for step 1, for skimming it, is you're looking for your verb, your action words. This says reacts to form, so that means the arrow is in the right direction, so we don't have to worry about that. If it says is produced by, then you'd be backwards, so you just need to be careful. So you skimmed, it's in the right order. So we start here with magnesium metal. Magnesium is Mg. Metal is telling us that it is a solid and is N plus. Sodium chloride is NaCl. Dissolved in water makes it aqueous. Reacts to form is just the arrow. Magnesium chloride is MgCl2. Remember your compounds, your ionic compounds. Magnesium is a +2 charge, chlorine is a 1- charge, so MgCl2. Dissolved in water still means that it is aqueous, and then we have sodium metal, which just means solid. So look at this. This breaks the whole thing down and turns it into chemistry. Now, we're not worrying about balancing yet because it's not balanced. Now, that same thing, this time more colors. Magnesium metal is MgS and is still a plus. Sodium chloride is a NaCl. Dissolved in water is our aqueous. Reacts to form is our arrow. Magnesium chloride is still MgCl2. Dissolved in water is still AQ, or aqueous, and is still a plus. And sodium metal is NaS. So as you can see, this one's broken down a little further. This is a more professional way to do it. The other one was going really, really slow. This is better. And don't worry, the third one is even more. This one's without arrows. Magnesium metal and sodium chloride dissolved in water react to form magnesium chloride dissolved in water and sodium metal. As you can see, translating it should be done at the beginning to the end, piece at a time, and you suddenly have your English into chemistry. Now, there's practice. You can go play with this. I'm going to leave that to you. Going the other direction. If I have the chemistry already and I want it in English, don't be fancy. Don't make your life easy. Start at the beginning and work your way to the end. 2 molecules, water, gas, become 2 molecules, hydrogen gas and oxygen gas. Specifically 1 molecule oxygen gas. So remember, we don't write the number ones. So again, 2 molecules water vapor or water gas become 2 molecules hydrogen gas and 1 molecule oxygen gas. Piece at a time, one and the other. And you just translate as you go. Since both sides have 4 atoms of hydrogen and 2 atoms of oxygen, this is balanced. Keeping that in mind, this is a balanced chemical equation. Notice it has no coefficient. We do not write the 1 there.